Okay, everyone, I think it's time. So I also want to thank everyone's participation, and it's our last lecture for second semester lecture lecture series. So today, on behalf of Professor Dong-Soo Lee, I'd like to introduce our lecturer, Dr. Jae-Sung Lee. Dr. Lee, actually, you will well know from our previous workshops and lecture series. He is currently the professor in Department of Nuclear Medicine in Seoul National University Hospital. He has dedicated to many researches and clinical application of nuclear physics, machines, and software. Today, Dr. Lee will deliver us a lecture regarding brain PET machine and software. So please welcome Dr. Jae-Sung Lee.
Thank you, Professor Sir, for your kind introduction. As Professor Sir introduced, I am Jae-Sung Lee, in the same, institution as a professor in Seoul National University, and I also, involved in the, company, the Attenuation imaging. That I will mostly talk about the product of this company today. The title that I was given is the brain pen, the machine and software. So actually so I will introduce our recent technology on the pen machines and the software in this term. So so as I told you, that I'm involved in the Attenuation imaging. I mean that I'm a co-founder and the CEO of the Attenuation imaging. So actually, I think I need to disclose my conflict of interest before starting my presentation. Okay. Here is the outline of my presentation. Actually, so today let me introduce mainly introduce our current technology of the Attenuation imaging. So that include the MR comparable PET solution for simultaneous PET MR. So that is preclinical machine, and the brain dedicated PET scanner. That is a kind of extension of our technology to the clinical system. Then let me briefly introduce you how we have developed the AI powered brain quantification software that is supposed to be used in the brain PET imaging research and potentially for the clinical application. So actually, Attenuation imaging is a company established there with a goal to provide the society with innovative biomedical imaging devices and the solution that is located in the Seoul, Korea. Actually, that we established this company in 2016, but actually, that we achieved very early the success. I mean that we provided our first machine MR comparable PET scanner to the NIH in the United States, and this machine is used in several US and the Korean institutions, including the UC Davis and the University of Arizona in the United States, and the Kiram's in South Korea. Actually, this year we also launched AI powered software for the brain PET image analysis, as I told you, and we are also developing the clinical brain PET scanner, so that would be useful for the low dose the brain PET imaging of the the dementia patient or something like that. So yeah, so let me start with the introduction to our preclinical PEDMR solution. Yeah, actually, as you know that the combining of PET and MRI, have several advantages, including the capability of simultaneous in vivo assessment of structural and metabolic processes. Another important advantage would be the perfect and spatiotemporal correlation of these the structural and metabolic processes. So that is possible because we acquire the data simultaneously without any delay between the PET and MR images. Recently, so these are the recent technical advances achieved in the simultaneous PET-MR solutions. So these technical advances would include total body total body mouse imaging capability with long axial field of view, and fast and real-time PET image reconstruction with the parallel computing, thanks to the advances in the GPU or something like that, and improved the quantitative accuracy of PET with proper attenuation correction of animal body and RF coil would be another technical advances. And physical performance of this advanced machines has been demonstrated through peer-reviewed papers. And stable supply of commercial product for simultaneous PET-MR imaging is also available. SIMPAN is the Brightonics the solutions to the simultaneous PET-MR imaging for small animals. Actually, it is based on advanced the silicon photomultiplier SIPM the technology for truly simultaneous PET-MR imaging. So with exceptional performance and total body mouse imaging, high throughput workflow, one-click acquisition and reconstruction, and real-time scan positioning and planning, and so that it can support for various models to the animal models and to support diverse MRI systems. Yeah, the simple system of the Brightonics imaging, small animal PET solution for the simultaneous PET-MR that has been combined with various MRI systems. For example, that it was combined with permanent magnet-based MRI of aspect imaging, and it has been also combined with ultra high field the MRI, such as 7 Tesla and 9.4 Tesla MRI. Okay. So you can see here the configuration of the simple systems. Actually, that there are 4 simple systems. I mean that the 4 simple systems are now available, and all of these simple systems use the LSO crystal with 1.2 millimeter crystal size, and the inner diameter of the systems is 6 centimeter or the 7.6 centimeter, and the axial field of view depends on the SIMPAN model. I mean that the SIMPAN X and SIMPAN XL has 11 centimeter axial field of view, so that is sufficiently long for mouse total body imaging in a single bed position. And these scanners has commonly very nice the spatial resolution and energy resolution. I mean that the spatial resolution of these simple systems is about 0.8 millimeter at the center of field of view when we apply the iterative image reconstruction algorithm. And the uniformity of spatial resolution is also quite good. I mean that the spatial resolution is less than 1.2 millimeter within 30 millimeter field of view. I mean that the radius of the field of view. If we apply the iterative image reconstruction that incorporate point spread function modeling. The energy resolution of this scanner, these scanners are also very excellent. I mean that it is about 10%. So you can see here the the example animal imaging. I mean that the mouse imaging acquired with the sodium fluoride. The sodium fluoride as a radio tracer. Yeah. So as I told you, that the SIMPAT models has high sensitivity and high good spatial resolution. And for example, that the SIMPAT X has 10.4% sensitivity of the radiation detection, coincidence detection. I mean, so that is why that we could acquire this kind of this imaging with very small amount of radio tracer. I mean that the both images were acquired for 10 minutes, but for the left image that we used the conventional amount. I mean the 270 microcurie. For the left image, the activity was on 4 microcurie. It was a very small amount. So you can see here the simultaneously acquired the PET imaging. They're using the Brightonics SIMPAT insert and glucose 9.4 Tesla animal dedicated MRI. So the radio tracer that we used in this study was fluorine 18 FBCIT. So that is a tracer for dopamine transporter imaging. Actually, that this images, PET images was acquired after 60 minutes after the tracer injection for 20 minutes with about 200 microcurie radio activity. The MR was T2 turbo layer the sequence data, and anyway that the both of PET and MRI showed very high spatial resolution and very accurate anatomical localization in the brain of the small mouse. Yeah, so let me, actually that based on this the advanced the silicon photomultiplier technology, so we are now expanding our product to the clinical systems. So the clinical system that we are developing based on the grant support from the Korean government is brain dedicated organ dedicated PET systems. Yeah, actually that so using this system, actually we can acquire the brain image of the patient in the sitting position like this to save the space required for the system installation. Okay. And actually that we can transform the position. We can change the position of PET detector head like this to allow the patient to scan in the supine position as well for the the older patient who has a difficulty in sitting in the chairs or something like that. Yeah, by the way, anyway that it require the minimal footprint for the system installation because of each compact size, and because we don't need any separate machine room for system cooling or the parallel computation or some image reconstruction or something like that. Actually, that we can also transform this system to have the detector position in this way. So if we in the place in PET detectors in this way, actually we can employ this system for the woman's the breast imaging, and that some additional peripheral imaging will be also possible if we turn around the patient chairs in this way. So I think that you can think about the further application of this system for your patient. Okay. Actually, that we plan to use the several AI technologies for this brain PET scanner. For example, that we have interest in the AI-based attenuation correction. Yeah. For example, that we developed the AI-based attenuation correction, in which we utilized joint reconstruction of activity and attenuation with the good time of flight information, measurement information, and that was combined with deep neural networks. I mean, so once that we acquired the emission PET data, actually that using the MLAA simultaneous activity and attenuation reconstruction algorithm, we can generate this initial activity and attenuation map. Yeah, but that the attenuation map acquired using only the emission PET data with the time of flight information has the poor quality in terms of statistical noise and the crosstalk artifact between attenuation and activity. So currently it is hard to use this attenuation map directly for the PET image attenuation correction and the scale correction. But if we utilize deep neural network, deep learning, actually that once this activity and attenuation map are fed into the deep neural networks, we can generate this kind of pseudocity. I mean that the AI-based attenuation map that is almost equivalent to the CT-based attenuation map. So actually in this two JNN paper, so we have shown that the accuracy of this AI-based attenuation correction is quite good. I mean that very high. I mean it yielded less than 5% error or something like that in terms of the SUV quantification. So we are now evaluating this method for the attenuation correction of our brain dedicated PET scanner. Now, another the AI-based technology that we will utilize is the AI-powered brain PET quantification. Yeah, actually that this slide shows the conventional pipeline for brain PET quantification. I mean that for example that for the accurate the amyloid PET quantification, usually we need MR based or the CT based the spatial normalization of PET images, because that the amyloid, for example, that amyloid PET has very different pattern of radio tracer between the patient and the normal control groups. I mean that the very different pattern of radio tracer uptake in the amyloid positive and the negative cases. So that is why that it is quite difficult to achieve accurate spatial normalization using only the amyloid PET data. So that is why that we need to utilize the MRI or the CT data of the same individual for the accurate spatial normalization. So in the most commonly used the quantification pipeline, first we co-register the amyloid PET and the match the same individuals in MRI, and then we perform spatial normalization of this MRI into the template space, then special the transformation parameter used in the MR spatial normalization easily applied to the amyloid PET data to acquire the spatially normalized amyloid PET. Once we generate this spatially normalized amyloid PET, we apply predefined brain atlas to calculate regional quantification result. Yeah, I would say that this is a very conventional method, but usually that if we use the famous SPM program, it takes the longer than 10 minutes or something like that for entire manual processing to acquire this regional quantification result. Yeah, but the new pipeline that we have developed is a kind of the one-click brain PET quantification. Actually, that for the spatial normalization and the quantification of the regional PET data, actually we don't need any MRI or CT data, because we perform direct spatial normalization of amyloid PET data in the standard space, we do know the transformation, we almost know transformation error or something like that. So I will show so what's the performance of this data in the next slides. Yeah, actually in this technique we also use deep neural network, convolutional neural network, that provide the deformation field of individual PET data into the spatially normalized PET. I mean that the neural network infer the deformation field once individual PET data is given to the neural network as an input. So finally that we apply this deformation field to the individual PET data to generate spatially normalized. Yeah, so actually that because that we perform direct spatial normalization without the CT or MR, we don't need any co-registration the procedure and the spatial normalization of anatomical images. So that is why that the computation time is very, very fast. I mean that it takes less than 30 seconds to provide image processing and the quantification result. And actually that this AI based the spatial normalization is very precise even for the images with the severe atrophy or something like that. As I told you, this is the quantification without MR images. So and it generates quantitative report in the PDF, JPG, or the CSV files. It is very user friendly, and it allows one-click ease to use interface, and support multiple types of PET radio tracers, including NeuraCheck and the Visual and the AmiVid. Okay. Yeah, so this is the interface of the software that Brightonix Imaging has developed for the amyloid PET quantification. So once you log in with your username and the password, actually you can use this program. Yeah, but actually the main program is installed in my computer, in our computer in the hospital. So actually we do not need to send the images to the cloud or any other places outside of the hospital. So actually it allows very secure the protection of our patient data. Anyway, that once we enter the program, actually that we can upload our image files from the local computer, or we can also connect to we can also connect to the PACS database to the utilize the PET images saved in the PACS servers or PACS database. Yeah. Anyway, once that we transfer or upload image files, this program automatically starts the spatial normalization of PET data. So the spatial normalization and quantification and the 3D rendering takes only 30 minutes, 30 seconds or something like that, depends on the computation, the power of the computer that we have. And once the spatial normalization is completed, actually spatially normalized PET data is overlapped with the standard ML template. I mean that the standard ML template provided by Montreal University Institute. And that the 3D rendered images is also flagged. Yeah, and then immediately after spatial normalization is completed, this program generate this kind of report. Actually that the SVR with the reference regions cerebellum or the pons as reference regions, it calculated in SVR for global brain, the global regions, and the frontal and parietal, temporal, and occipital regions. And it also provide the SVR for any other important the brain regions for Alzheimer's patient evaluations. Yeah, and actually that we also generate centiloid value. So that is a kind of harmonized value for various amyloid plaque image radio tracers. Okay, and although so these quantitative results can be saved as the PDF or JPG or the CSV files for the processing. Actually, that when we if we save result in the CSV file, actually that the quantitative result for all of about 100 the brain regions are saved in the CSV file, so we can utilize it for our further the research. And actually that this the spatially normalized image and the parametric image of SVR can be also the saved as the Nifty file. That can be utilized in the SPM and any other brain image analysis software. So you can perform a kind of the voxel-based analysis based on this the spatially normalized SVR parametric images. Yeah. We can also change the brain atlas. Currently we provide two different atlases, so you can choose what we want, and reference region can be also the selected among the cerebral gray matter and whole gray matter. I mean that the whole cerebellum and pons or something like that. So you may be curious how accurate this technology. So we have performed some the evaluation study by comparing the quantification result based on this the software. Actually, the name of this software is the BTX brain. So the accuracy of BTX brain was compared to the free software based the PET quantification. I mean that the free software is a very famous software for the MRI pixelation in the individual space, but it takes very long time. I mean that principal population require about 8 hours for each individual's brain image processing. But this population in the individual space is very accurate. So that is why that we used this free sample based the ML population and the ML based quantification as a gold standard for the comparison. And the pair quantification was performed using both of the SPM 12, a kind of conventional method, and the BTX brain. Actually, that for the SPM 12 the processing, we need the MRI as well as MRI, and the SUVR is calculated in the standard space. But the BTX brain is AI based image processing with no need MRI, as I told you, and the SUVR is also calculated in the standard space. Actually, this slide shows the result of spatial normalization performed using the SPM 12 with MRI and the BTX brain without the MRI. Actually, this is an amyloid negative case. Actually, in this case, that the ventricle of the patient was quite big. So, but the SPM 12 couldn't deal with this the large ventricle of the patient when we compare this spatially normalized image with T1 MRI template. Yeah, but as you can see here, the BTX brain provide very accurate result of spatial normalization. So this is another example. I mean that so this is the result of spatial normalization of the patient with the high uptake of amyloid. Yeah, actually the result was quite similar as in the previous case. This patient also has big ventricle like that, but the SPM couldn't successfully deal with these large ventricles. But the BTX brain was quite successful in the spatial normalization of this very challenging case. Okay, although we have not used any MR or the CT information. So this is the scattered plot. And x-axis is SUVR acquired using the FreeSuffer program, FreeSuffer based quantification that takes about 8 hours for each individual, and the y-axis is the SUVR calculated based on the SPM 12. I mean the conventional method using the MRI for the PET spatial normalization. So as you can see, that there is significant bias when we apply the conventional technique. But this blue line is for the BTX brain, based on the spatial normalization using artificial neural network without any need of X-ray CT or the MRI. As you can see, the significant improvement in the accuracy of the quantification. So actually, this was the result from the fluorobeta band, and this is the result using the fluorometamer. So actually, this line is for the SPM 12 that also showed significant error in some regions, but the BTX brain allow very accurate quantification. Okay. Actually the result was the same as for fluorobeta pill. Okay. And actually that we have also the extended our technology to the other tracers. For example, that this is the result on the tau bit, the regular tracers for tau evaluation. Yeah, so actually that the result was quite identical to what we have seen with amyloid PET data. Actually, the large ventricle of the patient couldn't wear matched with temporary. You can also find some significant error in the temporal lobes here, but you can see the BTX brain based on the artificial neural network could achieve very good accuracy of the spatial normalization, as you can see. Okay. So actually, this is the quantification result for SPM12 and the BTX brain. Yeah. So actually, let me sum. I'd like to sum my presentation with this short summary. Actually, I introduced some advanced technology that the Brightonics imaging has achieved. The first one that I introduced was the MR compatible PET solution for simultaneous PET-MR imaging, and the second one was brain dedicated PET scanner developed based on silicon PM technology of Brightonics imaging, and the last one was AI powered brain PET quantification software. So that will be available for, that is now available for the brain PET research, and will be available for clinical application as well. Yeah, so yeah, if you have the interest in this technology, I think you can visit the website of Brightonics imaging, or you can email me well, you can send the email to the address in the website Brightonics imaging. So especially you may have interest in the test of this software using your own data. So if you perform amyloid PET and you have interest in this software, I think Brightonics imaging can provide you a kind of the demo version for the your own evaluation. So do you have any questions or comment?
I think we can have a brief I'd like to know how many people are using amyloid PET imaging. So I have prepared some questions, whether how many people are currently doing the amyloid PET imaging, and just to know the circumstance, how many people are doing molecular imaging based like animal studies for mouse imaging or.
Yeah, I was curious how many the team members are performing the amyloid PET, and how much you have interest in evaluating this technology. So yeah, actually that we are also developing same software for dopamine transport imaging and the FDG brain PET. So so you may also have interest in the FDG.
Okay, I think we can wait like 10 seconds more, 20 seconds more for our participants for their answers for these questions.
Yeah, I think you can also ask some, the general questions regarding the, PET instrumentation and, PET image, brain PET image, analysis. So, yeah, I will be available for, answering those kind of questions as well.
Yeah, I will end up and
Yeah, seems to me, that about, the only 15% of, the participants are using the amyloid, PET technology now. Yeah, but I hope, that it will be, more extended. And about, half of you are, conducting the molecular imaging based, the preclinical research and has, plan to establish it. So, so please, let me know if you, need, any information on the, system and the availability in your country. And we are also, talking with, the Korean, the Atomic Energy Institution and KOICA, to establish a kind of, national project to support, this kind of, molecular imaging equipment to the, the Asian developing countries. So, yeah, if we will be successful in, receiving those kind of, grant. I think that it will be, quite useful information for you as well. We are trying. We are now trying.
would there be any other questions or comments regarding any kind of PET machineries and also softwares? I really appreciate Professor Jae-sung Lee's lecture today. Thank you very much. And as a user, I also have used the software, and it seems to be very easily, and it really helps me for interpreting the amyloid imaging. Is there other like plan? Is there plan for? Is it possible to apply it like for other imagings, like FDGs or FDG brain PET, or maybe tau PETs later on? Is there plans for the application in other agents?
Yeah. So yeah, actually, that as I show you, that this technology is now available for tau imaging, and our next product will be the quantification program for dopamine transporter PET imaging. I mean the FPCIT. That is widely used in Korea now. And then that another one will be in FDG. So actually we are preparing software for all of these for PET tracers, and we also have interest in the population spectrum quantification. Yeah, but I'm not sure how much the brain population spectrum is used in other countries. So yeah, I'm also very curious.
Okay, thank you very much. Okay, I think then we can a bit early, but we can end up today's lecture. And I think this might be the last for the second semester lecture series. And I'd like to inform that we will have a workshop at winter and we will have like 2 time sessions for the workshop, and we would soon inform all of you about what kind of the subject and the contents for the winter workshop. So thank you very much for everyone for this long all the participants for participating in our lecture series. Thank you very much. And again, thank you very much, Professor Jae-sung Lee.
Thank you. Bye bye.